In this lesson, we're going to take a look at the concept of superposition of waves and the idea of interference. So let's start off with the idea of what a wave actually is. So here we have a little sinusoidal wave, uppy, downy, nice curvy wave. Now, what a wave is it's a disturbance. It's an energy movement throughout a material. So if we were to look at the particular patterns or the particular particles within a wave, then we could have, say this is a particle here, it would be moved away from its rest position up to this maximum. This particle here would be on its rest position, where this red line represents its rest position. This one here would be some way displaced downwards. This one here would be still at rest, and this one here would be at maximum position, and this one here would be at rest, and everything in between. But we just fill that out. And this would generate a snapshot of what the particles look like at a particular instant in time as a wave passes through. Now, if another particle was to attempt to come through here, then you would have collisions, you would have momentum change, you would have all sorts of things going on there. But if another wave attempts to come through, well, waves aren't really objects, they're disturbances within objects. So this wave could pass through this wave without any problem whatsoever. The issue would be, though, for the particles that are actually being affected by this wave, that matters would become very different. Because let's put, say, this wave interacting with this wave, it's just arrived, and say we take a snapshot of it at this exact time here. Now, all these particles aren't bothered in the slightest because this second wave here hasn't arrived at these particles yet. But this particle here suddenly finds itself in a situation where this wave is attempting to push it downwards to this position, but this wave is attempting to push it upwards to this position. Okay, so what we've got here is we've got two attempted displacements. And as with any two vectors that are acting on the same object, we can resolve these and we can vector sum them together. So if I was to take the vector sum of this one, it would be a vertical positive this way, and it would be a vertical negative this way, and let's assume for the sake of simplicity that they're equal, then the positive upwards and the negative downwards would exactly cancel each other out, and the result would be that this little particle would in fact go nowhere. If we take a look at this one here, that the original wave is attempting to push it to this position, and the other wave is attempting to push it by that displacement as well. So you would think that it's going to end up here, but no, because remember we're doing a vector addition. So what we've got is we've got a vector downwards and another vector downwards that are adding together at this point to give a resultant vector downwards that is these two added together. As a result, we end up with our little particle, if I can grab it, ending up down here because it has to end up in a position that is the vector sum of the two displacements that are trying to make it happen. Let's take a look at another position. Let's take a look at this particle here. What happens to it? So it's been attempted to be moved upwards here, but is being moved downwards by the other wave to this position. So let's vector sum these together, and they look roughly the same in height. So we end up with a situation where this happens. Okay, but what about here? Okay, so let's say this one's attempting to be moved upwards by this distance. Let's get a little blue one in here, make it a little more obvious. And this one's being moved downwards by this. So we then need to do a vector sum here, which is this large negative plus this quite small positive. So let's move this down a little bit so that it overlaps. So the resultant vector is here. So we end up with this situation. And we continue this onwards and onwards and onwards, but hopefully, as you can see, our nice little up-down pattern that was quite well established here is now somewhat under question because of this incoming wave. And that's just for a particular moment in time. As this wave passes through, this whole thing becomes slightly messed up as the two waves overlap each other. And this is what we call superposition. Once the waves pass fully through each other, though, and they end up completely separate again, then all the little particles that made up this wave in the first place, or all the little particles that were affected, I should say, by this wave, will end up going back to their original shapes and positions. as they were on the regular shape of the wave, and you'll get that nice curvy sine wave pattern back out again. But as they interact with each other, the waves will do very weird things. And this is what we call superposition. And in superposition, what we have is the idea that the resultant displacement is equal to the vector sum of the individual displacements of each wave at any given point. That is basically the principle of superposition, that the resultant displacement acting on a superposed wave is equal to the vector sum of the individual displacements of each wave at any given point. So let's take a look at that in just a little bit more detail, because you're going to be able to actually build these waves up from the ground and actually take two waves and superpose them and add them together. So in this one, what I've got here is I've got a couple of waves, a blue wave and a red wave on the left-hand side of the screen, and on the right-hand side of the screen I've got the same blue wave and the same red wave, except they're in dotted kind of format here so that we can't see them just as well. But the green wave on top is what happens when you add these two waves together, when you vector sum their parts. So at the very start we've got the red wave and the blue wave are both at 0 vertically, so the green wave is at 0 plus 0, which is 0. At these little peaks here, we've got the blue wave at 1, the red wave at 0.75, so then your green wave up here will have a maximum height here of 1.75. And then what Excel is doing is it's sampling all the way along the line, and it's just simply adding the two y values together for each given x value to give a superposed wave. Now this is pretty handy because our waves are in phase, that they are the same frequency, and that they have a slightly different amplitude, so I can see one or the other. Okay, so that's handy. Makes life very, very easy for us. Just go add, subtract, and so forth. But this game becomes a little bit more interesting if, say, the amplitude changes a bit. So let's decrease the amplitude of wave 2 a bit. So the amplitude of wave 2 going down, the red one's got a little bit shallower. We can see that our green amplitude goes down as well. And that's sort of what we would expect, because we're simply adding the y values together. And if the y value of the red one goes down and goes down and goes down, then eventually the green one's going to go down as well. And if we bring the amplitude of the red one all the way down to 0, we've got a completely flat line. What you get is the superposed wave is just the blue wave, which makes sense because an amplitude of 0 means that the wave doesn't exist. It doesn't have any energy to give. As soon as the amplitude comes up, you will note that our superposed wave comes up. Here I've got the amplitudes exactly the same, and our superposed wave is a wave of double the amplitude, same frequency as before, same wavelength as before, but now twice the amplitude. Okay, so let's change the frequency of the wave. So let's make the second wave here a little bit more frequent. So it goes we've got 1, 2, nearly 3 full wavelengths in here, versus simply 1 a bit for the blue one. Okay, and you'll see that the superposition pattern has become a little bit more complicated here, because whilst we still have nice positive values adding together to give a good positive peak up here, our 0 point happens here, where this positive and this negative are equal to each other, and therefore we end up with a 0 position on there. Our low point happens not at the troughs of either of these two, but where they intersect with each other to give a low point there. And then it comes back up as the red wave moves into the positive. It's cancelling out the blue wave, goes 0 and stays 0 sort of for a period of time as these two waves cross over. Then we get the blue wave dominating to go upwards, and then there's a massive peak downwards, or a massive dive downwards, as the red and the blue both simultaneously go negative. Now, there's nothing for this except to just go point by point by point every so forth, and just add these two y values together. Excel does a great job of it because it's a machine and it just goes sample, 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 sample. In an exam situation, this is nightmarish, because if you go every 2 squares and plot your points, you miss the complete peak up here. If you go every 1 square, you probably miss the peak as well here. and you definitely miss this trough down here. So you have to try and think what's an appropriate sampling range. Now, when you've got complicated patterns like this, every quarter square is probably a good one to do, or every half square anyway. It's a good way to start going and then go, right, is there anything particularly interesting happening here? So interesting places are when one of them crosses the axes, because you know that the superposition point is on the other one. So when that one crosses the axis, the superposition point is here. When this one crosses, it's here. When you've got a cross there, you'll see there. So that's always a good place to start going, is where do all these ones cross the axis, because your superposed wave, you can plot a point on it. Equally, where the two waves cross over each other is always going to be very interesting, so plot those. And then if you see that you're supposed to probably have a turning point somewhere, so you end up here, and then your next point's down here somewhere, you can assume that you're going to have to turn somewhere. Having extra points to figure out where that turn is important. So exam technique wise, this is a difficult question. It's not tough mentally speaking, it's just adding numbers together. It's tough in terms of it's going to suck time, and that's annoying. Now, let's get ourselves back to a situation where we have similar frequencies again, and this time let's change the phase. If I could spell phase, that would help, so let's correct that spelling mistake. So let's change the phase of this object. So what I'm doing in terms of phase is I'm just shifting the red wave, and you can see that it's moving along a little bit. So instead of the two waves starting off at 0, 0, where they were and they were heading upwards at the very start, so they were nicely in phase with each other. Let's move them 90 degrees out of phase with each other. So move that so that we start at 0, 0. That's absolutely grand. But they're now one's traveling downwards, so they're out of phase with each other. Sorry, 180 degrees out of phase with each other. So pi out of phase with each other. In this case, what we're having is that the overall effect is to damp the superposition here, that the superposition is of less amplitude in all positions than it is in the two original waves. That's because they are out of phase, but they have the same frequency and the same wavelength. So at all times, positives and negatives are meeting each other. Right? If I change the amplitude to being exactly the same, what you have is a perfect destruction, and your superposed wave is gone. This is called destructive interference. Okay, the waves are coming together in such a way that at all places you get an addition vector-wise of 0. So you get 0 displacement. This is destructive interference. With slightly lower amplitudes, whilst it is still being destructive, it's not completely destructive. You still get some form of wave. If I move on a little bit, then let's put them a quarter cycle out, so somewhere like that. Okay, you'll see that we do get a superposed wave, but again, its maximum amplitude is not the same as just adding two maximum amplitudes together. You have a somewhat depressed amplitude because you are getting destructive interference. They're not helping each other perfectly here, but the pattern's pretty good because we have same frequency, we have same wavelength. Okay, so that's not too bad. If I increase the amplitude to double, we'll see that the maximum amplitude up here is about 1.5-ish of what the original amplitude would be. But the pattern's still pretty good. It's once I alter the frequency that things become interesting. Now, whilst this might look completely random at the start, as the frequency goes up and goes up and goes up and goes up, what you'll start to see is that the ups and downs follow the pattern of these match the frequency of the red wave, these peaks and troughs inside here, and the general smoothing of the curve follows the blue pattern. So you end up with something that looks like the red wave sitting on a pattern that looks like the blue wave, when the frequencies are very, very, very unmatched, and we have lots and lots and lots of red waves available, but very few blue waves available. Okay, and this is the concept of superposition. Right, so let's maybe try ourselves a little example as to what it looks like in a real world question. Okay, so we're going to flip back to our question sheet, and we'll have a wee look at what's going on here. So let's pop back into here. Okay, so here we've got two waves that are interacting in the same place, and what we'd like to do is find what is their superposition. So I'm going to grab the green pen here, and we'll make these line cells pretty thick so that we can see the points that are going on. And all we need to do is go along here and sample so that we get our shape. So here I've got 0 and 0 in the y-axis, so I definitely know there's a point there. That's maybe a bit too thick for the line, so let's bring that down a bit. We'll go across to point 1 here. So we've got just above 0.5 and just above 0.75. So my superposition is going to be about 1.25, somewhere around about here. And if I'm doing this properly in the exam, I've got proper gridded paper, I've got a ruler out, I'm doing all the right things. Then here's my maximum point here, so I'll want to definitely take a look at that. That's about 0.6, so we're going to go up to about here for our maximum point, something like that. Then we've got maximum point in this wave, which is about 0.75. That's about 0.8, so that's going to be about 1.6. Ooh, that might be a little bit higher even this time. So what we've got, about 0.75 here, we've got about 0.8 here. So do we think that's going to go higher? Let's put it there. Let's put it there. We've got a crossover here at 0.7, what looks like about 0.75, 0.75. So that's going to be a 1.5. So we're going to have a shape that looks a bit like this. Ooh, this is unpleasant, isn't it? Let's take a look at this one here. We've got a crossover at 0.5 and about 0.25, so that's going to give me a point here. And then, as we recommended, let's take a look at the x-axis ones, because I know that as this crosses the x-axis, this is the point here, and as this one crosses the x-axis, then this is the point here. So our shape looks to be up and over and down like this. Then at this low point here, we've got an extra 0.25-ish on the downward section. That looks pretty good there. At this point here, that's going to be even lower. So that's going to be a full square and a bit extra. So that goes to that, a full square and a little bit. So that's going to be that kind of low point there. There's about 0.6, 0.6-ish. So that's going to come to there. I think that's coming back up this way. Again, though, here. And then that square to that square is going to end up adding to right about there. Then we've got our x-axis cross. So that's definitely there. And we've got an x-axis cross over here, which puts it all the way up here. Right, okay, so we've got a lot going on in between here. So let's maybe figure out what's going on there. There's one and a bit up, one down, so that gives me a bit up. And you can see I'm just mentally adding these together. So we're getting this kind of shape going on here. Now what's happening over at this point, we've got, oh wow, look at that. That's going to go back up again. That's weird. Okay, let's take a look at that. We've got 0.5, 0.5, that's going to go just beyond 1. The question is, does it go up over there, or does it dip and come back up? Let's find out. Let's do the bit in between here. So we've got about 0.25 there. We've got about 0.75-ish there. So it looks like it's going to go up and over into that point. That looks about right. Then we've got a 1 and a 1.5 there. So that's going to bring me down to here. Okay, so we probably want a bit more details to what happens in between here. So let's take, well, we know there's an x-axis cross, so we know that it goes there. So we've got that kind of shape going on. So this looks like we've got a big peak here, then a big trough, then it comes up to a peak here, and that peak's going to be lower. What about this one? We've got 2 squares down, we've got most of a square up, so we're going to go down here, and then we've got an x-axis cross there, which means that my point is on here. Okay, so it looks like there's a turning point somewhere in there, because if that's 2 squares down and that a bit up, and the question is, what does it do in between here? Does it go across to this? Let's find out. So what's happening in here? We've got this far down, so that's what, 1 and a good bit, and then half a square up. So that looks like we've got a kind of turning point there, I think. And then this and this, half and half low, so it gives me about 1 there. And then I don't have any of the rest of the graph. So that's the best I can do. Now what I need to do then is put this together into some form of coherent line. This is where you wish you had a stylus, because we're going to have to do this by the mouse, but let's go for it. So we'll start at 0, 0. We'll draw our way up to this peak, round, down through here, then rounding up through this point, up to about here, down here, and around. And that's what I reckon my wave is going to look like, in something that does look as if I've had a severe hand tremor during my exam, but that's what I'm reckoning. I reckon it looks something like that. Okay, now handy if we had the actual answer. So let's go and get the actual answer. So here is the final answer generated by Excel. We have our two waves, our black wave and our red wave, slightly offset. And then the dotted green line is the superposition that we're meant to have. So let's see how we get on in terms of R1. So let's take this and just lay it on top. Okay, so the green dotted line should follow our orange one. And as you can see, the green dots are going pretty well through the dots that we picked. Our low point here is a little bit out, I think, and our high point here is a little bit out. I think all in all, for eyeballing it, we've done a good job. Now your job is to do the same. So if you look in the description below, you will find a little homework assignment that has 3 superpositions that you can go through. The first 2 aren't too bad, and the third one will give you nightmares for weeks. So have a crack at that. Let me know in the comments how you get on, and whatever you do, don't forget that physics rocks. It's true.